Beta is a unit speed curve, and sigma s is just the velocity vector of beta, so it just moves on the unit sphere sigma. Belki şöyle yapayım. Bunu başka bir renkle çizelim. Right? It's a curve on the sphere. Okay. Of course, sigma need not to be unit speed. Note that sigma is not necessarily unit speed. Indeed, what is the derivative of sigma? Well, that is the second derivative of beta, and second derivative of beta is what? It's a unit speed curve. For a unit speed curve, the second derivative is just the curvature times the normal vector, right? Okay. So that the speed of sigma is just the curvature of beta, right? The length of this vector, the speed of sigma is the length of this vector. And what is the length of this vector? N is a unit vector, therefore the length is just kappa. Therefore the speed of sigma is the curvature of beta. All right. What else? Well, we may just keep taking derivatives, right? What is the second derivative? Well, it is just kappa times n derivative. Here, both curvature and n are functions of s. So when you take the derivative, you get what? You apply Leibniz rule, derivative of kappa times n plus kappa times derivative of n prime. And then we can use Frene formulas. Okay, now what is n prime? N prime is okay, for n prime I can write this. N prime from the Frene formulas minus kappa times t plus tau times b, right? N prime. And then I have this term, kappa prime times n. So we get what? This is from the Frene formulas. N prime is equal to this. So we get minus kappa squared t plus kappa tau b plus k prime times n. So we wrote the acceleration vector in t, b, and n frame, right? Okay. And from this, we can compute the following. Let me switch to this board. Let me first erase it. This is not a unit speed curve, therefore to compute its geometric objects like curvature torsion, I am using the previous theorem, right? Because it's not unit speed. So All right. Hence, sigma prime cross sigma double prime is what? Sigma prime is just computed as kappa times n, and then cross product minus kappa squared t plus kappa tau b plus k prime n. Okay. Now we keep in mind that, you know, if this is the vector t, n is a vector perpendicular to this, right? It's a frame, and b was the cross product of t and b. So we use right hand rule. Right hand rule. So when you take the product, we get here, for example, minus kappa cubed, and then n cross t, this is t, plus kappa squared tau n cross b, and here I have n cross n, but n cross n is 0. What is n cross t? N cross t is minus b, right? This is just minus b, and n cross b, n cross b, it is just t. Okay, so this is t. Therefore, we get kappa cubed times b plus kappa squared tau t. Let me check with my okay, yeah. Or in kappa squared parenthesis, this is a scalar, so k times b plus tau times t. Okay. So, curvature of sigma, let me denote it like this, not to confuse with the curvature of beta. Okay, kappa sigma. What I mean with this, the curvature of sigma, of the space curve sigma. What is the curvature? Curvature was the length of this vector, right? Length of this vector divided by length of this gadget, right? For an arbitrary curve, space curve, regular, the curvature was this: alpha prime cross alpha double prime divided by alpha norm of alpha cubed. Now I have all these quantities. Norm of this, what is the norm of this vector? Okay. Well, this is a right triangle, right? I have this vector b, and I have this vector t, and in this vector, I mean in this directions, I have kappa and tau. So this is a right triangle, and I would like to find the sum, the norm of this. So from Pythagorean theorem, it is just right norm of this vector. So this is a positive number. I just keep it, and then length of this, which is squared, length of this vector squared, kappa squared, length of this vector squared, tau squared, and then okay. So this is just kappa squared times, sorry, kappa squared plus tau squared, and then sigma prime. Sigma prime was what? Sigma prime was k times n, right? Sigma prime was k times n. Its norm is just kappa, and then you have cubed, so this is kappa cubed. So what we have is just then, okay, this is gone, this is gone. I have 1 over kappa. It goes here as 1, and then here I have torsion divided by kappa squared. All right. And the thing is that this is always larger than 1 because it is square root of 1 plus something. And that's not, of course, unusual because this is a curve on the sphere of radius 1. And we know that if you have a curve on a sphere of radius a, then the curvature at any point is larger than or equal to 1 over a. In this case, the radius is just 1, right? It's a unit sphere. So we expect that curvature is larger than 1 over the radius, which is 1. So it is larger than 1. Değil mi? Bu kürenin üzerinde olduğu için yarıçapı a olsaydı curvature her zaman 1 bölü a'dan büyük olacaktı. Bizimkinin yarıçapı 1 olduğuna göre 1 bölü 1'den büyük. So covers well, but then it means that all the curves with curvature larger than 1 lies on a sphere. I don't think the converse should hold. Yeah, it's a too strong result. If it is constant, then we know that it's planar. No. Yeah, I don't know. If torsion is 0, then yeah, but otherwise, I don't think it's true. I mean, it seems too strong. For example, you know, consider a curve like this. You know, it just it's like a helix, but with smaller and smaller, you know, periods. Probably the curvature is getting larger and larger, but so it is larger than, for example, 1 over 2. Okay, but it doesn't lie on a sphere of radius 2. Okay. Sharp turns always, you know, gives you large curvature, right? Because sharp turn means it's a lot of acceleration. Right? Değil mi? Emniyet kemerini o yüzden takıyoruz. Bir anda değil mi? Dönerseniz veya durursanız fazla acceleration olursa fırlıyorsunuz. Okay. We have definition. A regular curve alpha in R3 is a cylindrical helix provided that uh, the unit tangent T of alpha has constant angle V with some fixed vector, unit vector. Okay. Fixed unit vector. Ne demek bu? The tangent vector and a fixed unit vector has always the same angle between them. So u is this, let's say this vector, u is this one. T makes angle v with u. So it is either like this or like this, or it just rotates around this. So it moves on a cone actually, right? How can we state this fact using vectors? Yeah, right. U cross T is what? Length of this vector times length of this vector, which are both 1, times the cosine of the angle between them. But that angle is constant V, so this is just cosine V for all S. Okay. So here, let's say we take alpha to be a space curve. All right. Consider the real valued function h of s defined to be beta s minus beta 0 dot product with g. So beta nereden çıktı? Okay. Beta is the beta is the unit speed reparameterization of alpha. And t is the tangent vector of beta, of course. Okay. Again, for alpha, the tangent vector, normal vector, and binormal vector are t bar, n bar, b bar. For the unit speed reparameterization, tangent vector, normal vector, and binormal vector are t and b. Okay. So we have this setup. So what does this do? You know, we have a curve, right? Something like this. Let's say this is beta 0, and at any point s, so you are at this point. So what you do, you look at the vector beta s minus beta 0. So you look at this vector and you take dot product of this with the vector u. Okay, let's see what we get. Okay. All right. So dh minus ds. So I take derivative of h. H is the dot product of beta s minus beta 0 with the constant vector u. Therefore, right, so this is dds of beta s minus beta 0 dot product with u. So I have this derivative of this. This is a constant vector. So if I apply Leibniz rule, derivative of this, which is just beta prime s minus 0 dot product with u plus this guy times derivative of this, which is just 0. So I have just u times beta prime s. And beta prime s is just the vector t, of course, because beta is the unit speed reparameterization of alpha, and the tangent vector of beta is called t, right? So we have this, and we know that this is by assumption constant. So this is a constant. Okay. Well, this means hence beta is rising at a constant rate relative to the arc length, and h of s this is a function whose derivative is this constant. So what should be this function then? Integral of this constant function. So it is just s times this plus a constant. So this is s times cosine v plus a constant, right? Just integral of this, entire derivative of this. But what is this c? Well, we know what? We know that h of 0 is just beta 0 minus beta 0 dot u, so it is 0. And if you plug here and h of 0 here, s times cosine 0 plus c. Cosine 0 is just 1, so this is s plus c. No. Oh, I am sorry. This is just S yerine 0 yazacağız ya. Okay. I am sorry. We should write h of 0. H of 0 is just you write 0 for S, so it is just C. Therefore, we see that C is 0, and hence H of S is just S times cosine V. Okay? H is just S times cosine V. Okay. Well, H was beta S. Okay, hence H of T is just S of T times cosine V. Here, we are using the fact that S is a function of T, right? The distance traveled or arc length function. Okay, now this means what? Okay, this means the following. If let's say U is this vector, remember U is a vector given to us, right? It's the vector so that alpha prime alpha has the tangent vector of alpha or beta makes a constant angle with this vector U, and that angle it was V. So U is a fixed vector. Sorry? Yeah, it will turn out to be that. Yes, you're right. So we have some, from this, we have such a picture. Let's see. Okay. We have something like this. And our curve always makes a constant angle with the vector U. So if I write, you know, if I draw these lines parallel to U, our curve beta or alpha, it is the same curve, just reparameterized, is something like this. And this angle is always the same. So this angle is constant, okay? And h of s in this case is just s times cosine v. Okay. And here is a result related to this, which characterizes this cylindrical helix curves, a regular curve, alpha, not necessarily unit speed, with positive curvature. We require that the curvature is positive, is a cylindrical helix, if and only if tau over kappa is constant. So that's the result. Okay. In our case, yeah, we didn't do that computation. Okay. So this is a nice result, right? If you know these two quantities, if the ratio is just a constant, let's say always 3, then you know that your curve is a cylindrical helix. What's a cylindrical helix? It's a curve so that its tangent vector makes a fixed angle with some given vector. Okay. If you just take, for example, this vector to be the z-axis, so what this tells us that the tangent vector of your curve makes a constant angle with the z-axis. Okay, so it is going upward with a constant speed. Tamam mı? Yani yukarıya çıkma hızı sabit. Merdiven gibi. Yani basamaklar hep aynı boyda. Ona denk geliyor. Ama merdiven illa circular olmayabilir. Yani şöyle garip bir merdiven olabilir. Değil mi? Okay. For an helix, we know that both curvature and torsion were constants, right? So this is something more general. For an helix, regular helix, both of them were constants. I don't remember now what were. One of them was like a B over C. Hatırlıyor musunuz? Let me see. Yeah, okay. Yeah, if it was usual helix, then kappa was A over C squared and tau was B over C squared. The curve being beta S was what? A times cosine S over A times sine S over A, and then ds over oh no, this is not A, these are C. I'm sorry, C. And C was, as usual, A squared plus B squared inside square root. So for a circular helix given with this formula, both curvature and tau were constants. Therefore, this ratio is also constant. So this theorem is a generalization of this result, which tells us that if these are constants, we know that well, we don't know. We will see that if these are both constants, then it has to be a helix. But this theorem tells us that they, even though they may not be constant, if the ratio is a constant, then this curve is a cylindrical helix. So it's a generalized helix. Okay. All right. Let me see how much time do I have. 10 minutes. Okay, let's see if I can prove this in time. Oh. Okay. All right. So now we may assume that alpha has unit speed. Okay. Uh, we have already seen if alpha is a cylindrical helix, then tau over kappa is constant. Helix width, let me say, t dot u is cosine v, then cylindrical helix means this is constant for some fixed vector u and fixed angle v, and just taking the derivative t dot u prime, we get t prime dot u plus t dot u prime, but this is a constant vector, so it is 0. So this is just t prime dot u. And what is t prime? This is a unit speed curve. So from Frena formulas, this is just kappa times n dot u. And since we are given that the curvature is never 0, it's always positive, we see that right, this product is 0 and this number is not 0, therefore this is 0. It means that n is also is always perpendicular to u. N is perpendicular to u. Okay, so namely n dot u is 0. Okay, thus for each s, u lies in the plane determined by TS and BS. Why is that? So whatever S is and S dot U is 0, so NS is a vector and U is in the plane perpendicular to N, right? But we have already two vectors perpendicular to N, which are B and T, right? So this vector U is perpendicular to N, therefore it lies in the plane spanned by T and B. So U is somewhere here. U is constant. U is constant. All these vectors might change. However, U always lies in the plane spanned by V and T. Yani bu düzlem hareket ediyor olabilir ama her zaman U vektörünü içinde tutuyor. Yani U vektörü bu düzlemin içinde kalacak şekilde düzlem hareket ediyor. Tamam mı? Dolayısıyla da hani U vektörünün etrafında dönüyor gibi düşünebilirsiniz. Değil mi? U vektörü her zaman bunun içinde. So this plane is kind of turning about the vector U because it always has U vector in it. Okay. So we may write it this way. We may write it, you know, let me draw the coordinate plane. T and B are perpendicular vectors. Let's say this is the vector B and this is the vector T. U is a vector, unit vector in this plane. So we look at this angle, whatever that is. Let's say it is V. Then U is what? U is just cosine, pardon, şunu T almışım, bunu B almışım. So it is just cosine V times T plus sine V times B. Değil mi? Bu plane hareket ediyor ama B ile T vektörü her zaman birbirine dikler. Dolayısıyla her plane'de bunlar bir koordinat sistemi veriyor. Bu vektörde o plane'de olduğuna göre şöyle bir equation'ı sağlamak zorunda. Burada V de şu açı. V is the angle measured from the axis T. All right. Now let's take the derivative of this expression. So this is constant. So take DDS of both sides. To get this is 0 because it is constant, and then I take derivative of this. This angle is also constant. Why is that? Because we assume that the angle between the tangent vector of the curve with the vector U is constant, and V, right? It's a spherical helix. T dot U is just cosine V. So this is just, since this is constant, this derivative is just cosine V times T prime plus sine V times B prime. And we apply Frene formulas. This is cosine V times T prime is just kappa times N plus sine V times beta prime. Beta prime was what? Beta prime neydi? Minus minus tau yok minus minus tau n plus t. Şöyle mi? Ha, B yok. B yok. Şu yok. Sadece bu. Minus tau n. Tamam. Tamam. N prime'da 2 tanesi var. Peki buradan ne çıkar? Alright. So this is just n is a vector. So I have cosine V minus sine V tau times the vector n is 0. This implies this coefficient must be 0, right? Because n is a unit vector, it is never 0. Therefore, if this quantity is 0, this coefficient must be 0. So, tau'nun bunlar ya unit speed curve'in şeyleri. B prime sadece minus tau çarpı n. V yok orada. Alfa eğrisi için tangent, normal ve şeyleri şunlar alıyorum. Unit speed olduğu zaman TNB alıyorum. Burada alfayı zaten unit speed aldığım için şunlar yok. Sadece bunlar var. Peki, this coefficient is 0. This means what? This means kappa over tau is just tangent V, right? Okay. So, in particular, this is constant, a constant. Sıfıra eşit dersek cosine V kappa equals sine V tau. Dolayısıyla kappa over tau is sine over cosine. Bu da tangent. Tamam mı? Peki. Okay. I'll do the remaining part on Wednesday. Yes. Let me stop. Oops. Zamanında geçirmişim.